All right, sorry, I'm going to have to do it the old-fashioned way here. So this is another chapter in the book. It's the ablation properties of polymer nanocomposites. And some of that work was actually done here at Texas State. I'll draw attention to that because we do have a rocket motor room down the hill from here. And so they actually did some of the testing here when it was done. And some of the testing is also done by Dr. Tate in engineering. So you'll see that as well. Okay, there we go. So what are we going to use? What do we use ablation materials for? It's not like something you want to just have for, just rubbing tribology. It really has to do with high heat, high pressure, and usually in the case of rocket motors, rocket nozzles, there's actually solids in the stream. So you can imagine these ablative materials need to do one, try to form some kind of crust, some kind of outgassing that's going to give us an expansion, and that outgassing, that releasing of gases releases heat. So you're having less heat transfer through your material. And so as it wears away, new materials exposed, and then new gases are generated, new materials exposed. And if you designed it right, you'll get all the way to the ground before you run out of material. Okay, so that's going with that. The ablation rate is really important. So we're going to talk about that. But they're also using rocket nozzles. Rocket nozzles, especially solid fuel rocket nozzles, have composite materials in them, and they use aluminum as the fuel. Therefore, they spit aluminum oxide out the nozzle. And so that is very ablative on the surface. Plus, there's a high pressure inside of it, and then running through the threshold of the nozzle, which gives it its thrust, and then it expands out into the lower pressure outdoors. And so there's high pressure, high heat, and a whole bunch of ablating materials. And then also for some internal insulation on propulsion systems. And I'll show you some pictures of those as well. So there we go. So, okay. So in a solid rocket motor, what you have is the solid propellant. It's burning at an interface. Okay. Now, this is a simple one. Most of the time, you actually have a hole running all the way through your propellant, so it'll burn more and give you more thrust. But there's also areas during this combustion zone right here that this is where it has been burning through. And the gases are actually sitting, the highest peak is the nozzle right here. That's where the highest pressure differential is, and that's where you get your thrust. But as you have these combustion gases flowing across it, the heat is going to give you it's going to start out as your just regular material right here, and then it's going to start to burn it. And then when it burns, it's going to start to heat, it's going to transfer through, creating gaseous materials. And so this charred layer tends to expand as you go, okay? And it tends to leach out all of the organic material. And so you're just left with whatever non-organic material, non-combustible materials that are there. And hopefully you have some kind of secondary structure so that when the solids that are going across ablating it are also going to not heat through this system as well. And for almost all of our systems, we want it to, during the full burn, like for example, a Sidewinder missile runs for 63 seconds. So you want to have at least half of your liner material still there after the full burn. I used to work at the Navy base to design the Sidewinder missiles. So then we have an insulation layer, and then this is usually steel. They're actually moving to a composite one. It's called Bluetooth. And then this is the external airflow. So this is kind of where we're looking at. And so we're looking at the material as a protective layer and a disposable layer. It's a one-time use only thing.
So why does it need half the layer?
Safety margin. You make it twice as thick as you think you're going to need. Because if you burn a little hot, or if you got a tear, you got some chunk fly out one side, you don't want it to burn through the wall. Because if you burn through the sidewall of this, then guess what? That's another jet, and it doesn't go where you want it to go.
Like SpaceX, aren't they like reusing the thrusters? So are they?
That's a liquid. That's a liquid rocket. It uses liquid hydrogen, liquid oxygen. You cannot you cannot reuse solid rocket motors. Okay, so this is the nozzle, and this is a highly decomposed nozzle. And really, most of the time you have your nozzle's going to be out of metal, then you're going to have an insert. This insert has to be something else. This has to be the high ablative material right here. And so if you look at this would be one of the inserts that you can use right here. It's got a cone shape. This is the inside, that's the outside. The outer flange hooks to the outer side. This is the actual flare of the cone. This gives you, the size of this cone is directed by how much thrust and force you're getting. You need to have it not too big and not too small to get maximum thrust. So the idea is that by the time you get out to this edge, you've had all of your thrust prepared and the pressure differential is almost zero here. So you actually want this pressure balance to happen. But that's why this place right here is where the highest heat, the highest pressure, and the highest concentration of particles exists. And that's where the ablative materials are actually used. Okay, so let's talk a little bit more about the nozzle. This is a cross-section of a test nozzle. And so it's steel all for this stuff right here, but then this is the composite that you would, this is the insert that you would be testing. So usually these are a lot of fiber reinforced materials like phenolics, carbon fiber phenolics, and carbon composites, where they take fiber carbon composites and center them to get all the organic material. And so it's gone through a secondary process. Okay, and so the ratio, if this changes, if this ablates too much as it's going, the thrust will go down because it'll start opening it'll worn it down enough to open it. So that you really have to have this material be designed specifically to hold that diameter for the maximum amount of thrust for the entire burn of your rocket. Now they're also used in liquid rockets as well, but I'm going to focus on just ones used in ablative of the solid rocket motors, because the solid rocket motors have a lot of solids actually coming through the nozzle. Okay. All right. So how does a solid rocket motor work? Okay. I sold this from let's see, Rocketdyne. Anyway, so inside a solid rocket motor, you'll have a tip on it. Then you have an ignition source right here where it's going to start it burning. Notice there's a whole tube here. It's going to actually burn across this entire surface area, generating gases and solids at high pressure. It shoots through your nozzle here. Notice that right here is where you have, you're going to have probably the grain, which is the combustible material here, the propellant here, is going to burn first through here. And so you have to have this as an ablative material as well, so that it doesn't burn through the case. But way up here, it's not going to be burning there very long. So the protectant can be much thinner. You can actually just have the metal wall. So then the propellant here is usually mixed with a butadiene rubber. I'll show you several different formulations. It's usually aluminum powder, ammonium perchlorate, and a binder, which also burns. And so it does create some CO2 as well. And it's done in a consistency about a hard rubber. It says a eraser. And you know why?
Why is that consistent?
Consistency is very important, but it won't crack. You don't want it to crack, because if you crack, you're changing the surface area. If you change the surface area, you change the thrust dynamics. And that's why solid rocket motors blow up. Is if you have a crack anywhere in here, what it's going to do is it's going to burn into that crack. And then you're going to be closer to this edge than you should have been during burn time. And you're going to either burn through the side, or it will actually explode because it will create so many more gases that it comes to the nozzle. So you'll see all of these solid propellants are going to be real gummy and elastic materials. And it's actually easy to process them that way too, because you use butadiene and styrene, and then you process it. And it's used to use planetary mixers that would do this to mix it. Now they're using ultrasonic low shear mixing to mix it. But the largest rocket motor I saw fired while I was there was a solid rocket booster for the space shuttle. It burned for over a minute. It was a minute and like 20 seconds. And the thing is 8 feet in diameter. So they had to strap it to a mountain horizontally.
So the space shuttle is solid.
The two outside ones are solid rockets. The big thing in the middle is the liquid fuel for the main thrusters. But the two outside parts, I'll show you a picture.
So you're saying such like styrene and butadiene, are these just combusted?
Yeah, they're just combusted there through
So
there.
there's no solid afterwards? It's just
Not with the carbon. Most of the carbon burns in the ammonia it breaks up into hydrogen and stuff. It produces a lot of HCl from the perchlorate, and then it produces aluminum oxide. So, what goes into the shuttle propellant here? This is by weight. It's about 70% ammonium chloride by weight, 16% aluminum by weight, aluminum metal. Then a catalyst, that's a combustion catalyst, iron oxide there. Butadiene acrylonitrile rubber is about 12%, and then the epoxy curation for this there. And so we have, if we had a 10,000 pound rocket right here, or propellant grain, which is one of the ones that goes into the space shuttle, 16% of that, or 1,600 pounds of it was aluminum, which is going to produce 2,400 pounds of aluminum oxide as it comes from the nozzle. So bigger is more is harder. Okay, so the outside ones on the space shuttle here are the solid rocket boosters here. This is liquid fuel and drives these main thrusters here. Now this is a launch tower here, and notice these big clouds here. Okay, those are clouds. That is water, even though they dump 300,000 gallons of water in 41 seconds. It's HCl, aluminum oxide, and also a bunch of other combustibles. But the reason it's white is the aluminum oxide. And the reason they flush the entire tower down is because all the HCl given off during burn of the chlorate, they have to wash the tower down with 300,000 gallons of water. And then they have to neutralize that water, and then they have to pump it out into the Florida swamp. So that's another reason we need ablative materials here. So the classical one is just your carbon phenolic. So it's a phenolic resin. I'll show you the structure later. Using carbon fibers, and you can do different orientation patterns. I've seen actually a really cool one where they started with a crisscross pattern, but then they did an on-edge pattern right at the nose cusp. So it was ablating actually on the front surfaces of the fibers. Then the carbon-carbon composites typically are the phenolic commons that have been centered so that they have most of the organic baked out of it. So you have a carbon matrix binding the carbon fibers. But we're talking nanocomposites, so we're going to do something a little different. Okay, so in the book, there are all these different things. I just wanted to draw some attention to. So we have montmillinite clay, we have Kevlar fibers, we have polyimide microparticles, we have EPDM, which is a rubber. We have some harder things like nylon, thermoplastic urethanes, silicone rubber. Those are all different things that have been used to try to get new ablative materials. But by far the most successful have been the sets of phenolics. So a lot of the stuff we'll see is phenolic, but I will start with a nylon 6 one. Okay, so let's talk about what we call thermochemical equation. Okay, so this is kind of what we were talking about before. You have your virgin material here that hasn't been heated by the heat flux. You have your stream coming out here. It's high heat, so you have radiated flux in. As it hits the first top layer, it decomposes and outgasses a little bit. And then the layer below it decomposes and outgasses. That puffs up the stuff. That's the chars. And puffs it up more, puffs it up more. And so then now that we have all this stuff that's decomposed completely, we have enough heat flux to continue to decompose and continue to outgas pyrolysis gases, which are small molecules and CO2, et cetera. And then we have the next thing we have is this is the stream of air as it's heading across here. There's a layer right across here that's going slower. It's like when you push water through a pipe, the water along the walls goes slower than the water in the middle of the pipe, right? So we're having that same thing happen here. But what's also happening here is this is actually getting bigger and bigger as it ablates, because now we also have our solid particles running across it, and wearing it off. And because there's such high shear and flow here, you have any molten products in your char, they're going to melt and flow in the direction of the gas flow. Okay. So for each of these thermal protective systems, that's what TPS is for. We're going to end up with something with a huge char layer. We're going to end up with some of it gone. It was here, it's gone. We're going to end up with a char layer, our pyrolysis zone, and some hopefully virgin material on the bottom for our safety measures, our engineering science. Okay, so I need to move that bar to the bottom. So in this right here, this is the results of using montmorillonite clay in the nylon 6. So that's a ring opening nylon, it only has one function group here. And they clearly show this is the surface of it here. This is the char zone. See how it's kind of foamy area? Then this is the reaction zone or the pyrolysis zone, or the decomposition zone. So it's changing in its color and density compared to the virgin material. So this is still mostly solid, but it's starting to get porous. This is highly porous. And then the surface has actually been ablated. This particular one is in using a direct force. So they have a rocket motor shooting directly at it and it's orthogonal. So we don't see the flow in this particular picture, but toward the edges, you can actually see streaming. And I'll show you a couple pictures of that. And if you blow up the layer, well, here again, this is the char zone with the large holes, the large barriers that help keep it thermally insulated. And then the reaction zone is starting to get expanding a little bit, and the virgin material looks like a nice piece of nylon. Yes.
Why is the reaction zone necessary? Why is that?
Well, because, okay, the stuff on top is already reacted with all of the heat, okay? So this is the heat that's soaking through to the virgin material. When you started, the entire thing is virgin material. First layer, you got heat, and then that forms a char layer, and you're still soaking heat in. So you're not having a direct contact with the gases, but you have a thermal decomposition of the material. So your reactive zone or your pyrolysis zone is where this has enough heat flux to start decomposing, but it hasn't completely decomposed to be non-permeable materials, which is the char layer. So it's in the process of becoming a char layer. Does that make sense? Okay. Okay. Okay, so let's dig a little deeper in there. What they did here is this is the surface of this is 5 weight % of chlorosite 30A, and chlorosite 30A is quaternary ammonium salt modified clay to make it easier to get into materials. And so what you'll see here is on the top layer here is actually, you can see that the little white edges are the montmorillonite that's left over after the carbon stuff burns away. Okay, and so as we go further in here, this actually you might be able to see the montmorillonite stuck in the matrix here, but the white edges are the part that didn't burn off, it stayed there as that char layer.
So just to understand, the reaction zone, then that's the actual fuel? Or like what?
This is the part that is decomposing and giving off gases that cause foaming and gases that cause cooling. So it actually helps cool it. It helps draw heat away from that zone. But it's the actual polymer itself going through thermal decomposition.
So this is all on the out. This is all the outside.
Correct. From where the heat is being delivered this way, you first have your char layer, your reaction zone, and then your virgin material. So it's going. You're looking down through the thing as it's being burned. Okay. So in this result here, they wanted to do a kind of comparison. So the speed of the gas running through there is Mach 0.13. And then they had a low mass flux, which is this 12. So what they're saying is that they're blowing hot gases with aluminum particles in it across there. And we're looking for how much it ablated. And if we're looking at here, this is your erosion time in mils per second. Mils per second. So notice these right here, right there. No virgin material remains. That means it burned through. That's bad. That's a fail. Okay. So then this is here. This is 5 of the mils per second with the low mass, and then as we go to higher and higher, especially higher loadings of these right here, we get into the 5 range here. The phenolics and the EDPM are actually better than any of those at that low flux. If we look at the high flux, we actually get a different thing. The phenolic resin can't handle the heat flux. It's decomposing faster than the system with the 5% chlorosite in it. And so we actually have significant better numbers at this high flux than at the low flux, right? So, and that's 0.4 pounds of aluminum oxide per square inch per second. So, and I'll show you how they do that. I have a picture of the rocket motor for that. Okay. Okay. And so they also went in and wanted to make sure that their monazite was actually dispersed in there. I believe this is the 5% right here. So they actually had a pretty good job of exfoliating. You can see they're all kind of lined up behind. And they processed it, I believe, through this is through a twin screw extruder. They did a master batch and then we did a batch to get the 5%. So you wouldn't think nylon would be one of the best ones for that, but they did do okay. Okay, this is another paper right here where we're going to do EPDM, which is ethylene propylene diene monomer rubber. Usually it's butadiene, but it's there. When we're going to use Kevlar filled, okay? So that's a common thing to use Kevlar as the support structure and use the rubber to help do it. There's actually a reason rubber works well as an ablation material is because instead of being hard and getting it scratched off, you can actually have the ablating material just bounce off elastically. And so it actually can wear less. Unfortunately, that works really well in lower heat environments. I don't think it works very well in this heat environment. So they made a couple different things where they had just the neat polymer by itself with the carbon nanofibers and with 10% carbon nanofibers. And they saw that they could extend out the decomposition here and extend it out to closer to 600 or 700. So then they said, okay, so we can see that this decomposes, and we can see that these decompose at different rates in different speeds. Notice one set is at the 5 degrees per minute, the darker line is at the 5 degrees per minute. The lighter lines right here are at the 50 degrees per minute. So they're saying, oh, you know, it's going to have faster heat flux when you see it in the rocket motor. We should try it faster. And so they got those results and they said, okay, it's working. We should continue to study this. And so they took a picture of it here. And this is at the 5 degrees a minute. And they see that there's a lot of see how there's a lot, it started as a smooth surface. So some of it has ablated away. The Kevlar nanofibers have pyrolized. And so they're now in that state, and there's nice porosity in the system that you see from it. So that was at this is at 15 weight%, I think. No, yeah. And then when you do it at the faster heat rate, you see that there seems to be a thicker char layer. So it's faster heat flux. And so there's, oh, that's going to be closer to what a rocket motor would do, right? Because it's giving us this char. Well, then they went off and ran an experiment with an actual motor, and they calculated that the rate of heating of this motor, it's a 4-inch char motor. So it's basically, they power it with liquid diesel and shoot it at your sample, and it's 4 inches in diameter when they do it. And they calculated the heat flux to be 150,000 degrees per minute. Okay, so rocket motors are a lot higher, right? And notice this looks completely different. We have the nanocomposite, the nanomaterial is charring on the edges here. We have a lot more porosity. We have a different structure here. And notice we have flow. So you have a little bit of flow that you can see it's all going kind of in one direction. So we have that melt phase happening as well. Okay. So then they did it where they did another one with the carbon nanofibers exposed to the heat rate. And then they did it another one with just the Kevlar at 50. That didn't look any worse. And then they did it with the rocket motor. And the rocket motor looked completely different than the two others, the 5 degrees a minute for the TGA and the 50 degrees a minute TGA. When exposed to this 150,000 degrees per minute, right here, we get a completely different structure. You have pyrolized fibers, a lot of porosity, a lot more. It's eaten down into the cave. Your surface roughness is much higher. So what did they decide? They decided that TGA is not suitable to test the ablative materials. So saying that the results from the TGA never got close to what the ablative, what the rocket motor showed. But they proved that they can do the scaled rocket motor samples, and that they couldn't not do the rocket motor. And let me tell you, rocket motors are much more fun than TGAs. Okay, so that was their conclusion. So I thought that was really neat that they admitted that we didn't think this through. So. All right, moving on to the next thing. We're going to talk about thermoplastic polyurethanes here. And on this one right here, we're using, it's actually a polyimide-based silicone. It's put out by Dow. It's one of the Dow products, and they still make it. I looked it up today. And so it's really neat because when you cure it up, it's really low viscosity. You cure it up, and then it can be really, really tough. And this is the image of the char layer for the nanosilica particles. So they took this thing and added nanosilica particles. So the thing you notice here is that, number one, we have porosity. You want porosity in your char layer. This is going straight down, and so you can't actually see the bubbles underneath. But these are like larger bubbles underneath where the little holes are. And so we see a nice consistent layer across the surface. We see nice porosity. We see it was outgassing properly during its ablation.
So it's a thermoplastic, but then they cross it.
It is, I want to say it's cross-linked, yes.
Well, yeah, it says vulcanization, wasn't it? So but they did.
Yeah.
They started with thermoplastic.
Yeah. So yeah, they started with a thermoplastic elastomer, and then they vulcanized it. Yes, said it. So if you kind of go through there and look at it, image of the char layer with instead of the nanosilica using the organo-modified montmorillonite flow site, probably, they actually ended up using that to blend it into a two-screw extruder. So it's processed through the extruder at a low enough temperature to vulcanize and then bake it out in vulcanization. And so what they see here is that the structure is a lot different. The actual silica starts to melt and flow on the surface. And again, this is from the top. So if you look again, go back, we have a nice, almost uniform flat surface with the nanosilicon, but with the montmorillonite, which is an aluminosilicate, we have a different structure to it. And so you can almost see on the edges, maybe where the montmorillonite is starting to aggregate and gather together, because all the other stuff is burned away. Okay. So they made sure that they dispersed this well in the dark phases are the montmorillonite, the light phases are the are the polyimide.
Well, you can go to more, and then it'll find the
Oh.
more.
More
It's higher floating controls.
and hide
That's it.
one
More.
there. Okay, thank you. Escape to show more. Okay, that's it. Okay, so the dark is the silicone phase, actually, because at the higher mass, the lighter color is the polyimide phase. And so they can see these are the little these are the montmorillonites that are dispersed in your phase. And it looks like it's dispersed more in the light phase, which is the polyimide phase. Okay, but it won't let me. All right. And so this is that with the montmorillonite. Okay, so the other one was virgin. This is with the montmorillonite. You can see the montmorillonite aggregating in there. You can't really see it in these, but there is montmorillonite in the dark phase as well. So it's both suspended in the silicone phase and in the polyimide phase. And so it's actually pretty well dispersed in the system. Okay. So what are the results of this? Well, okay, so if they took just the polymer or just the EPDM with the Kevlar in it and looked at its ablation rate. So this is ablation rate 4 mils per second, 9 mils per second, or I'm sorry, 7 mils per second and 8 mils per second. And then when they did it at different speeds, so they're doing it at different speeds of hot gas and fluid process. When they looked at the one with the montmorillonite in here, it actually had a lower starting at 3 mils per second, but at higher loadings, at higher rates, it was ablated faster. Huh. So it did okay at low when you had lower heat flux. But as you raise the temperature and raise the speed of the gases flowing across it, it did poorly. It's like the soft phase was being pushed or moving. Okay, so then they did it with a different derivative. This is, I want to say like a POS type structure here. They saw a similar behavior where the lower speed gave us a better number of these. And so, but then their best one was when they added this is a different type of filler. It's not monoclonite. They got it to be not so bad. But in all cases, at the higher Mach speed, it performed worse than the stuff they were. That is a POS. This is a carbon nanofibers. Okay, so the results are that yes, we came up with something, but it didn't work as well. Okay. But they did show that they got the flow side dispersed in there really, really well. These are all of the lowest concentration, 5 to 10%. Getting some bundling, but pretty good exfoliation, especially in that 2.5. There's almost no bundling at all. And then when they went to look at the carbon nanotubes, which are multi-mole carbon nanotubes, they got pretty good dispersion. Again, they got some bundling here at the higher loadings that we've seen before. And then but a lot better dispersion with lower weights. So they didn't make the composite well, it just didn't perform as well as they had hoped. Okay, so this is what we're going to look at. We're looking at heat in-depth temperature. So one of the things your ablative material does, besides erode away, is it also insulates. And so they did a measurement of 3 different places inside of the material. So what they did was they took a material and then they put one near the surface, one I think 5 millimeters down, one 5 more millimeters down. Okay. And then they ablated from the top and measured the temperature differential between them. So you have these right here, and they started at something like 25 degrees. So we see the one that they're trying to compete with here had at 10 millimeters in after a 50-second burn. Yeah, I think it's 50-second burn. It was 50 degrees down here, about 85 degrees there, and about 175 degrees on the surface. But what we see in the nanocomposites is we have the same performance with clay. Carbon nanofibers actually are higher in thermal conductivity. You could have expected that, right? When we use thermal carbon nanofibers for thermal conductivity, it actually helps draw heat into the system faster, which is why maybe it doesn't perform as well, because your pyrolysis zone is so far in that you're outgassing, you can't perform foam action. And then we saw the same thing with the carbon fibers and with the multi-wall carbon nanotubes. It's a little bit higher, but not as high as the carbon nanofibers. Carbon nanofibers are longer, have a longer persistence length, and therefore can heat travel faster through the system. And they weren't looking for heat transfer. Notice also that the carbon nanofibers were 20%. So it was the highest loading, and it's probably the highest thermal conductivity filler they used. So that accounts for that change, that shift in the temperature range between those systems. Okay, and this is what they look like when they burn. So it's a sample, it's burned on top. You can see this is where the center of the jet was in these systems here. On that one there, you barely can tell where it was, but that's the base material right here. The clay did pretty good. It has some surface cracking, but it seems to have not flowed or changed much. The multi-wall carbon nanotubes, lots of surface cracking, and there's a divot here. So they're actually wading into it at the site there. And this is the carbon nanofibers right here. And so this is all done with a oxyacetylene torch burn. So they have the torch sitting here. So you have very big ablation area, very high charring on here because of that higher heat transfer. Higher heat transfer did not help. In the base material with the Kevlar fibers, those don't transfer heat as well. But the clay did okay.
So were they going for the higher conductivity, or were they hypothesizing?
No, they were using it as, well, it's already pyrolyzed, it's not going to burn, so it's going to help. So they didn't postulate that they were trying to do more thermal conductivity. The idea is you want that pyrolysis layer to get all of the heat so it can actually generate gases. Okay. So they looked at the surface of the Kevlar after the system. What they see is some melting of fibers. This is large masses of fiber. Notice everything else is burnt out. You're left with mostly carbonized material binding your Kevlar fibers together. Your Kevlar fibers are pyrolyzed to some extent as well. And so you see these pyrolyzed materials. And when they looked at they didn't do that. All right. So now they did a study where they looked at the polymer itself and what its mass loss is. And so that's right here. And then as you're looking at these nanocomposites, what we see here is that they have a higher mass loss at low loadings, and then they start to come up and get higher. But notice this is still a higher mass loss than the one with Kevlar. Okay. Now, in the case of the carbon nanofibers, we have a huge loss to start off with, and putting more of it in kind of levels it out a bit, but it still doesn't get close to where we saw there. And notice these were only filled 2.5 to 10%, but the carbon nanofibers were all the way up to 20%. So that's why their curve is extended at 15. So this also proves the fact that you have such a high mass loss early on that it's not helping your system. Okay, so this is a different type of rocket motor that we see in a couple other experiments. This is actually exactly like the one we have downhill. And so what this works on is you have an oxyacetylene torch. This is oxygen acetylene right here. It starts the torch, but then you have a hopper on top to put in your aluminum powder. And so the force of that, you can see the hose right there. This is the hose where the aluminum powder comes in, shoots out the nozzle, and then you vary the space between them. By varying the space, you can actually get different speeds or different heat fluxes. And then you have your thing bolted or clamped down to where you burn. Usually you use a burn time of 50 seconds, if that's a typical rocket motor burn time. And then you analyze the surface. So this is a different setup than what they used. They used an oxyacetylene torch. This is actually set up to actually do ablative materials testing. Okay. Okay, and so this is the difference right here. This is the data we got from the ablative testing, not just the oxyacetylene torch. And so we're looking at material recession. That means how far did it burn down? Okay, how far did it burn down? And so if we have the low loading here, we have about 6. Once we get to the higher loading at 5, it actually goes almost down to 2, and that kind of levels off. So why? Why do you think that it kind of leveled off? You have less of that charred polymer to act as a binder, carbon composite binder. And so at some point, it's just going to be all play and it can't stick together for a while. So you're going to see that happen a lot. And then with this right here, you see that same dip in the multi-weld carbon nanotubes. And again, both of those seem to have higher losses, probably due to the thermal flux. But the montmorillonite here performed quite well compared to that. And yeah, it even performed better than the EPDM. So this is actually finally got a good positive response. Okay, and then this is looking at your temperature rise internally at different things. So this is 5 millimeters from the surface, 10 millimeters from the surface, and 15 millimeters from the surface. They did 1,000 watts. Basically, they calculated what the heat flux would be 1,000 watts for 25 seconds. So you're heating up to this point, and then you stop heating. And then you're looking at the surface temperature rises to 180 degrees. The one that's below the surface, then we have less heat, and we have barely any rise in heat at all at the 15. So we're looking at it as a good thermal insulator, even with a high heat flux. We're seeing that it has very good, this is the 10% montmorillonite. This is the one that performed almost the best on the ablation testing as well. So they're showing that it has good thermal barrier properties as well as good ablation properties. Okay, so once you ablate it, what does it look like? So we have the top one here is the looking at the char level as we increase the amount of montmorillonite from 5 to 7.5 to 10 right here. And we'll see that it has kind of a weird texture to it, but notice it has porosity, it has surface texture. It started as a smooth plastic surface, and now we have what probably is being left behind is montmorillonite bound by carbonized polymer system. And then if we look at the lower magnification, we look at the different surface roughnesses here. We see the surface roughness texture as it's ablating down. It's just like, you know, the polymer is burning out from below the montmorillonite. It's just kind of collapsing. All right. And then what they found when they looked at one of the systems is they zoomed in really far and they saw these little beams. What happened? Actually, it turns out that I've seen this phenomenon before when I did nickel, pyrolyzing nickel for lithium-ion batteries. And what happens is the montmorillonite is actually decomposing and melting. And when it melts, it turns into little spheres and it cools back down. Decorative spheres of molten silicate. So the heat flux was so high that it actually melted the montmorillonite. So these are little spheres of silicates. Okay. And they saw the same structure at different loadings as well. But notice here, we're going to see them, it's a little bit different because these are still dispersed into this kind of porous matrix. This porous matrix made up of montmorillonite that didn't melt. And I'm going to say those were silicon, nanosilicon. The anode ones. And you'll see that they have the spherulites. And so even at the low loadings, you'll see them. And then at the higher loading, you get much bigger bumps. So that's the downside of that, but it again, this is one use only. So as long as it worked for your system, that worked. And then this is where we have looked at the carbon nanofibers. The carbon nanofibers behaved a little differently because the carbon nanofibers, because they'd already been pyrolyzed once, they are not going to burn again. But look at the mat type structure. As you go with just a little bit here in the higher mag, you have that surface texture. But then you look down here and you see the network of the carbon nanotubes that are holding up the system, the char layer. So that char layer is getting thicker with non-pyrolyzed material. So again, it should have done better, but it's just pumping too much heat into the base right here. So what are the conclusions? Overall, they said the 5% multi-wall nanotube performed as well or roughly as their baseline metrics, but it was outperformed by the montmorillonite clay formulation. I agree with that. The carbon fiber material also performed well at all metrics. I wouldn't say that, but was again outperformed by the montmorillonite clay. So clay wins this battle. Okay, questions on that? So obviously, not thinking about the heat transfer of the the carbon nanofibers was probably their biggest problem with this. The multi-wall carbon nanotubes, if they're short persistence length, they're not going to transfer heat as well, and so that might be why it performed better than it did. But the montmorillonite clay has a low thermal conductivity, which led to that higher resistance of heat flow, which led to higher properties. Okay, so now switch gears and go to phenolic nanocomposites. So in phenolic nanocomposites, they usually use phenol and formaldehyde, and that bakes out into a phosphate polymer microstructure on the form. And in this one, what they did was they used a octavinyl POS molecule here And what they got was phase separation, because if you look at this right here, as you do different things, like this one right here has just carbon black in it. See the carbon black's kind of all distributed. Not too bad, a little bit of clumping. This is montmorillonite. We did a very poor job of exfoliating the montmorillonite, but they have at least some of it is spread out right here. This is carbon. Carbon nanofibers right here. Commercial grade carbon nanofibers. This is the one with the POS. Notice the globules here. We have phase separation. POS is phase separating out of the phenolic material. And then this is when they dissolved it in IPA salt, they actually saw again phase separation. A difference in that system. Okay, so then they tried to say, okay, our montmorillonite should be better than that. So they tried to disperse it a little bit more. And again, they got very poor dispersion. We call this poor dispersion. Large platelets here, some exfoliation here. They're probably not using a good method. They were just using a stir method in their system. And so that was not appropriate. For this, they stirred it in IPA for 30 minutes and then added their materials. Okay, so now they mix their stuff in, and so they have different things, and then they also added a little bit of aluminum oxide. So we're going to use a standard phenolic mat, and they're going to not use the standard mix of the phenolic resin that already comes on it, but they're going to change a couple of things by adding three different materials in the system and then look for their erosion rates. So if you look at the erosion rates based on heat flux right here, heat erosion percent. Okay. At 1,000 heat flux, they all completely disappeared. 100% failed. 100% erosion. Okay. So in the system here where you have the, what's MC? Multi-walled carbon nanotubes, no carbon molding compound. That's the bare matrix by itself is molding compound. You're right. And then they've added a 2D and an SH. With SH they did a 60-degree shingle, and with the 2D they used 2D fabric. And then they added nano aluminum. So one is the as-is material that comes in. Second one is using orthogonal stacking method. And then there's the 60-degree stacking method. So in this case, they all failed. In this case, the lower heat flux, the as delivered failed, and these two were better because they had lower performance. And at the lowest heat flux, the two composites were actually better, but not much better than the actual stuff. But notice that, there's right here, even at this heat flux, this material is fixed. So we did get marked improvement.
So 60-degree shingle, is that 60 degrees from the normal to?
No, it was where they do them like this. The fibers go in this direction, in this direction, they're stacked at 60 degrees. At the two-dimensional is 90 degrees. And then as the regular ones are just straight fibers. Those are commercial products. The MX 4926. Okay, so they got enough good results there that they said, okay, we're going to do a rocket nozzle test. Okay, so they were able to get their materials. This is the material as is. It's the molded compound that has chopped fibers in it, and so it can be molded into this. So this is where it has the nanoclay incorporation. This is where it has the carbon nanofibers, and then this is where it has the aluminum oxide. You'll notice the color changes here. Nanoclay really didn't change it very much. Carbon fibers made it black, and the aluminum oxide made it black. So when they went and tested that, what they do is they use this kind of test bed right here. And so most of the machine is just built as is. You have some test equipment here. You put a plug of propellant here, you can ignite it. You have this, if you're testing insulation, you put the insulation here, you back it with another piece of metal or foam. If you're testing the nozzle, you put the nozzle here, and then you burn for a consistent test. It's usually about 8 seconds right here. Generates about 800 psi in the chamber, and so 800 psi in the chamber, and then as soon as it comes out that nozzle, so with this system here, what they're going to look for is what it looks like on this face, where it was being ablated from, and on the back side face. Did it flare out? Did it burn there too? So you're looking at the total diameter change as well as any surface change on the system. Okay, so what that looks like when it's happening, oh, I don't have that slide. Oh, that's next. Okay, is after you burn them, like here, here's the kind of structure you get. So again, this is the inside here. All your gases are coming through here and going through the orifice here to create thrust. And you see a lot of this surface has this whiter wood right here. That's mostly probably the montmorillonite being not blown off the surface here. This is the traditional molding compound with the carbon fibers in it. You see that it has a different surface texture. They both see some ablation, but these are pretty consistent. I think this nozzle is actually slightly small. We have, I'll show you on a table. But the other two looked really bad. The carbon nanofiber one had a buildup of aluminum oxide. Okay. It's blowing aluminum oxide out there. It could be in the molten state, could be in the solid state. So what's happening here is the carbon nanofibers are sucking so much heat from the surface. The aluminum oxide is embedding in something. That's the aluminum oxide from the pellet, not the film. So I think what we have here is that, again, heat transfer is being a problem with this. Yeah, and it did crack.
So if we use the best insulating material, then I think that is the only contributing factor to this.
It's not just that, because you have to have something that's decomposing, off-gassing, pyrolyzing. So it's good to have things that don't off-gas, but you don't want to overload it. You still need those gases to create that foam. That foam insulation layer is very important. So you couldn't just do a solid ceramic or something like that. Okay, so what I saw here, and this is what they're doing, is they're looking at the sample thickness as a dimension from the center. No, from the outside edge. So they're starting at the outside edge and going into where the hole is, where the nozzle is. And they see that they have here sample thickness actually went up on here. Why did it go up? Foaming. So we had foaming, and it didn't get ablated off of it much either. So we see expansion on these. This is the normal. This is with the one with the closed side in it. You see more expansion in all of these. We actually start to see wear on the other two. Right here, the white one is again the normal one. And then by the time we get here, all of them are getting down, are burning, or losing mass at that nozzle. So they're all losing mass. But the montmorillonite clay performed pretty close to the standard material. But notice the montmorillonite clay system foamed higher and probably insulated more. Okay, and so this is a cross section of the one with the carbon nanofibers here, the one that did not perform. And so what they were looking at is the face here. This is the inside, this is the outside. And they were looking at the wear along here, and they saw that there's a large amount of this aluminum oxide material bound to that surface. And but the wearing in the system here was bigger than other montmorillonite actually performed quite well. Okay, so let's look at our control here. Okay, so they looked at the, they did tensile data on these materials, and they saw that this is the control right here, where it is heat stress and tensile modulus right here. Adding the clay, we would expect it to have increased heat stress. That's the clay units of it. Didn't help the modulus that much, but it did help with the stress. And the other two materials with the two different other loaders, these are both carbon nanofibers, actually tanked those properties. So there's just too much carbon fiber there, not enough matrix. Okay, So let's shift gears again. So play one on that one too. So, all right, this is different. This is a phenolic with a kaolin. Kaolin is chlorosite and montmorillonite are charged clays, aluminosilicates. Kaolin is low, doesn't have so much charge on it, and so it's kind of easier to disperse. And again, we're using a phenolic resin, and this is a Novolac type phenolic resin. They basically just have a catalyst with formaldehyde and phenol. It makes the cross-link matrix here. They disperse the graphite in solution in isopropanol first, and then they interpolate methanol, and then so they got it dispersed first in the system. The montmorillonite is actually dispersed by shear. And what they see here is on A, this is after the testing here, on the top surface, the montmorillonite is giving us a spherical particles. Spherical particles, they're melting and putting together. And if you go in here, this is where the pyrolysis zone would be, and then this is probably closer to the heat flux direction. So this is on the lateral surface. So A is the surface right here. C and D are the side here, here, and here. So at the surface, you see a lot of damage. But on the side, as we're moving down, we have a little, this is in the pyrolysis zone, this is out of the pyrolysis zone, this should be in the bulk virgin material zone. So we see a big difference in the system as we go through the system, through the thickness of the materials. So in this one, they used glass and silica fiber phenol. So the glass is probably the one melting and causing little droplets at the top. They used a standard material, which is it's commercially available material, 31% resin, 61% chalk strands of silica, and then they added and it also contained micron-sized silicon particles. So the micron-sized silicon particles were also percent. But then they added 5 and 20% nanosilica, thinking that they're going to change the property, change the heat flow by having the nanomaterial in there. Okay. So when we look at this again, we see that we have the glass fibers are melting in those little balls right here. So let's see. BMC1 is 0% of the nanosilica, and BMC2, which is the middle row here, is 2% nanosilica. We actually see, they actually do a cross section of the ablation cone. You can see how far it burns down. We see a smaller ablation cone in the 2% loading of the nanosilica. And then this is a surface of the 8%. Notice that the 8%, there's a lot more melted stuff here, but there's also less ablation. So just that nanosilica is changing the dynamics of that glass melting problem. Getting it to improve its depth of ablation, at least. Okay. And so this is how they actually tested it. They had their samples and they had flat round samples and they were on the stage. Then they hit it with the heat flux. They chart it through there. And then they, this is the jet from the, this is the jet from the oscillator. Hit it from the top. Measured inflation where they. And so you can see that when you have there, you have that bubbling liquid glass on the top of it, right? So that glass melted and aggregated. Which is not a bad ablation mechanism. Okay. So then, moving on to the stuff here at Texas State, they were trying to take an additive to the standard phenolic with the carbon fiber, and they decided to use the molding compound as a rayon precursor for carbon-based fabrics to detach phenolic. And then they used a mil-spectrum phenolic. Then they used carbon nanotubes, multiple carbon nanotubes, really tiny, 10 to 15 nanometers, but pretty long, 1 to 5 microns long. So what they were looking for here is they were looking for the average recession in length, which means how far did it burn down in the system by adding carbon nanotubes. So right here is where we start with none here. So during the burn test, it burned down a little under a millimeter. Okay. And then by adding a 0.5%, they have really wide error bars. But they averaged it out to 0.6. And then with 1%, you got even lower, but way over here, 2%, you have got one smaller error bars, and about the same as the loading. So overall, they think that the 2% is the right level for having this additive in their carbon phenolic composite. So all I've done is change the standard setup by adding 2 weight percent carbon nanotubes. Okay, so if we look at that heat flux we have here, in the standard material, we have 500 millimeters and 10 millimeters here. Surface temperature 700 and 5 millimeters, it's 300 here. But with the 0.5%, we have a dramatic drop, only 400 degree surface temperature. And the internal temperature is about the same. We see a slight drop in adding more. So in this case, why isn't more nanotubes causing this harm?
Because it's coming from the top and they're oriented to the side most likely.
Well, the carbon fibers are oriented to the side, right? The nanotubes are dispersed in the phenolic
Maybe due to the length.
vapors. It's something about length. They haven't met the threshold to do thermal transfer. They've met the threshold to do electrical transfer, but not thermal transfer. They're not touching enough to get the heat transfer. So they're all acting as isolated little islands. And so if they upped it to 10%, you'd have the percolation threshold for thermal transfer. And you would see different, you would see them go up. But because they're below that thermal percolation threshold, it doesn't transfer the heat. Remember the one loading that we saw that had that high heat transfer, that was 29% carbon nanofibers. Okay, so that has to be high enough to transfer heat. Here at this loading, we don't. They're not high enough to transfer the heat. Okay, so this is a different one. This is a different one looking at a phenolic, but then they're starting with a graphitic felt. So basically, you can pyrolyze this graphitic felt, or you're starting with a graphite-based foam. And then they're going to fill these and look at their different thermal transfer, different ablation properties. Okay, and on this one, there are different little things where they're going to do carbon felt with long fibers, carbon felt with short fibers, phenolic resin, and then they're looking at adding carbon nanotubes, nothing, nano alumina, multi-wall, multi-layered graphitic adhesive. So it's basically clumps of graphite. So it's graphene that haven't been separated. Nothing with short fibers, and then nano aluminum. And they're going to look at their different properties here. So nano aluminum is competing against carbon nanotubes and graphites, graphite particles. Okay. So what you can do is you can make these things. And if we look at the first one, it's the long fiber felt that makes this fluffy little block brick here. And the fibers are not oriented in any specific order. And then this is the short fibers here. So those have longer persistence length than these. These have the shorter one. But I thought it was neat that they actually showed the foam thing. Okay, so this is different. This is not like the rocket motor test. This is the oxy-ablation. I'm sorry. This is the acetylene torch ablation test. So it's the OTB, oxyacetylene test bed. And it has a fixture that holds this here, and then you have a time state. And again, it's clamped down your sample here, and it's going orthogonal to the system. Gases are washing across it. That kind of thing. And so what you see here is in the center is where you get the highest amount of ablation, but then there's a ring of where it's high heat flux, and also stuff that's been moved off. And then by the time you get out here, most of the heat and or gases have dissipated, so there's less damage. So you'll see that kind of pattern in the system. Okay, so what their conclusions were is that the improvement on the blade performance was relative. They improved it and improved the char characteristics. So basically, having those nanomaterials in there, specifically the alumina, it gave it so the top was alumina particles, and that actually had a positive effect on the char making. They uniformly filled the materials with the nano-aluminum specifically, and the uniform inorganic char at a relatively low fraction. So what they're saying here is that only 5 weight %. They got it well dispersed, but that was what ended up on the surface when they looked at the collections. The ablative materials multifunctional properties because it improved it decreased thermal conductivity, it increased the insulation ability, and it made it slightly lighter weight than the carbon stuff, and it also improved resistance. So that was a win-win, right? And the ablation mechanisms were studied in those nano structure ablators. So the idea here is that just with that one system of 5 weight %, they saw improvements in properties that led them saying, okay, so their next paper is going to do 7.5, 10. See how much they can get in there. All right, questions on that?
Why do you get the like secondary ring?
The secondary ring?
Yeah. Like,
Oh.
because you have the where the torch is, right?
I know. No, I
Just like
talked too
one-
fast.
just one-
Okay. Okay, let me do that right here. Okay, so the first ring here is where you have the highest velocity of gases and the highest heat. Okay, so that's where you're going to get the worst of it. The outer ring here, this is a lower heat flux, and you have gases actually streaming horizontally. So here, they're hitting down, then bouncing up and going horizontal. So this zone here has a different heat flux and a different gas flow.
So it's like skipping over all that stuff.
It's not skipping over, it's still, as the gases are shooting up this way, there's still depositing heat there, so there's still heat. And by the time, so most of the heat was deposited by the time you get out to the outer ring. This area is still heated up, right? But it didn't heat up, decompose the matrix. So you're seeing, just as this is just where you're actually doing a lot of ablation, here's where you're just decomposing the matrix. And then here you go. Okay.
That was for the film.
This is for the foams,
For the foam.
the foams, yeah, the felt, yeah. The felts where they infused it with the film. So, and then this particular one, you couldn't, I don't know which sample this was. It's just gave it that result. So what they found out was that the clay actually did help their system. I'm sorry, the nano alumina helped their system slow down ablation. And it's redone. So I'm gonna stop recording. Okay, let's see. I need to do escape to get it back.
I have a question.
Okay. Yes.
For you mentioned at the beginning of propellant, like polymer with aluminum in it.
Yes.
Essentially, is it considered a composite?
Yes.
Have they ever tried to make nanocomposites?
Yes.
Did it have any effect?
No. You'd think it would because it's such a fast process, you know, that it would have there. I actually have published improving liquid rocket fuels without materials. Because if you use a material that absorbs the radiated heat, it heats up the droplet faster and burns faster. So, but that's technically just a nano solution. I probably won't present that.
I remember back in the day, I took the kids to go to see Houston and NASA. They had the capsule, the very first one that came from space and landed back on Earth. And it was like ceramic tiles.
It's a carbon ceramic. It's a carbon fiber infused with a resin, and then they take that out. They send it back.
Remember said they were white.
Oh, okay. So, okay, that must have been a really old capsule.
Yeah, it was like the very first one.
I think they moved away from the ceramic because it cracks, and so they went to the carbon composite.
Yeah, they had that one explosion.
The ceramics actually have a slight benefit, in they tend to be less dense, believe it or not, because they're slightly foamed. So they actually are a little bit lighter, so they might have stuck with it. But the newer, more modern ones are they have these cool winding patterns because they want to go in the direction, they want the fibers to be in the direction of the flow, so they're not abraded on the side like this. So they have a bunch of cool things. All right, well, that's ablation. See you on Tuesday. I don't know what I'm going to do. I think I'm going to do the nano energetics then. I'm trying to find a really cool slide I had for that. All right, I'm going to stop share.